Well, there are other elements where the situation is actually reversed, and we have too few neutrons for the number of protons that we actually have. So let's see, do we have an example here? Yes, the example is fluorine 18. Fluorine 18 has 9 protons, and it has, actually in this particular case, I think the normal isotope of fluorine is probably fluorine 19, so it's kind of short. It would actually like to have 19 neutrons. It doesn't. It only has, 10 neutrons. It only has 9, so it's got 9 protons and 9 neutrons, and it makes it inherently unstable. So what it does now, it's going to flip one of its protons and convert it back into a neutron. That's going to cause its atomic mass, its atomic number, to fall by 1. In the other case, we saw it actually went up by 1. Now it's going to fall by 1, and so it's going to be 8x18. And if we look at 8, the 8th element is oxygen, so it's going to go to oxygen. Well, in this case, we saw before that in the case of beta decay, we had to actually flip an up quark into a down quark in order to make it into a proton. We flipped the down quark to an up quark in order to convert a. Did I say that right? Let me see. I have to write that again myself now. I have to remember. So we have three quarks, 2/3, 2/3, and 1/3. So these are the positive ones, plus, and minus. So in this case, we have the proton. This is the proton, and in the neutron we have two downs and 1 up. So we had 2 downs and 1 up, and we flipped one of them to give us 2 up and 1 down. That was beta decay. Now in this case, we're going to go the opposite way. We're going to go from 2 up, 1 down, and we're going to flip that and get 2 down and 1 up. So we're actually going to be converting a proton, which is this one, into a neutron, which is that one. So in doing that, this still has to balance out. So now we can put the beta, if we put the beta back in, we have to show that it's actually a positively charged particle called a positron. And if we want to do that in isotopic notation, I'm going to remove the beta plus, and I'm going to write that in again as an electron, but this time it's a different kind of electron. Rather than being -1, 0, it's 1, 0. Now this will sum up. So this is the symbol actually for a positron, for that, and we would call that positron emission. And it's going to be important, we're going to see later on when we actually talk about, in a later chapter, when we talk about some of the radiodiagnostic tools that are available in medicine. We're going to be looking at those kinds of things. Okay, so let's see, where are we now? Okay, that was, we talked about positron decay. There's another one that you should know about as well. It is referred to as electron capture, abbreviated EC. And what electron capture is a little bit strange. So we have an atom, and let's see, we have an example here. It's gallium. So we have a gallium atom. Gallium is Ga, and this particular isotope of gallium happens to be radioactive, and it's radioactive by electron capture. So it shows the isotope is gallium 31, so we know that there's going to be 31 protons in here. I'm not going to draw them out, I'm just going to write 31P. And there also are, it has an atomic mass of 67, so that tells me that there are 36 neutrons. And there are, again, these shells around here, and there's 2 protons in here, and there's 8 over here. 2, 3, 4, 5, 6, 7, 8. And of course, it doesn't look like this. And those of you that have studied chemistry know that we've got s orbitals and p orbitals and d orbitals. And if you don't know that, it's not really necessary for this argument. But I want you to realize that this is just an older model of the atom, but it's just a little bit easier for us to envision it this way. One of these inner shell electrons actually can be emitted or actually absorbed by the nucleus. And when that happens, it's possible for that electron to be absorbed by a proton and create a new neutron. So what that's going to do is it's going to give us a nucleus that's going to have 30 protons in it, and it's going to have 37. Did I do that correctly? I think so. It's going to have 37 neutrons. So it should be an element. Yes, I did do that correctly. So if we write that element, if we write that in isotopic notation, so we had gallium, initially, gallium 3167. And we show it actually absorbing this orbital electron. And so we're going to get, as I said before, we're going to get something with 37 neutrons in it and 30 protons. So we put the 30 down here. In order to find the this number, we have to sum, what was that? That was a 67. I'm sorry, you can't see that. This is 6, 7 here. We have to sum now these two, so that's still going to give us 67. But the element that is 30, it is X 3067, is actually the element zinc. And so this is showing us that gallium converts to zinc by electron capture. So that is another form of radioactivity. And finally, we've got something called gamma decay. Gamma decay actually involves, when we had these alpha particles, which are pretty large particles, when they actually are ejected from the nucleus, it leaves the nucleus in an energetically excited state. There's kind of a recoil when that occurs. If you know anything about momentum, you realize that when you lose a piece of mass like that, there's going to be, it's kind of like you're throwing something out. There has to be some energy on the other side where you're actually going to maybe be pushing your nucleus is going to actually move a little bit, and that's going to set up a series of vibrations, and they're very, very rapid vibrations. And the energy that's actually given off by that vibrating nucleus is in the region of the electromagnetic spectrum that is the gamma region. So we have a gamma, and we don't, since this is electromagnetic radiation, there's nothing we can write here in terms of isotopic notation. This is, if we did want to write it, it would be just 0 and 0. So gamma is not actually going to change the mass of anything. But nevertheless, gamma particles, gamma rays, and that is the only really, of the things that we've talked about, is the only true form of electromagnetic radiation, is gamma. People sometimes use the terminology alpha rays and beta rays. Alpha and beta are really particulate. They're not really rays in the classical sense of the word. As I say, they're particles, and gamma is the only one that really is a ray. They also use the word in your book metastable, because sometimes when the alpha particle is kicked out, you get something that is, you get this excited state that doesn't immediately necessarily release gamma radiation, but it is in what is referred to as a metastable or metastate, and these metastable states are sometimes abbreviated with the letter M. So you'll find that the synthetic radionuclide technetium, when Mendeleev first created his periodic table, there was a space for an element having atomic number 43, and could never really find that element. And years later, it was actually synthesized in a cyclotron. Can be made in a nuclear reactor as well. But this element 43, technetium, was originally called masurium, M-A-S-U-R-I-U-M, but we refer to it as technetium today. and technetium is a radioisotope that is actually made from molybdenum, from a isotope of molybdenum by, I believe, by neutron bombardment. Nevertheless, technetium will exist in a metastable state, and it will then decay to a still radioactive state of technetium, but that will actually give off a gamma photon in the process. So that technetium 43, technetium 99, technetium 43, 99, in the metastable state, it's written as M, 99M, and that would go to 43 technetium 99 plus gamma. And again, the technetium itself would further would probably give off a beta particle and would convert to something else after that. Now, everything we talked about so far are what we would call these nuclear transformations that we've talked about are what we would call nuclear decay reactions. There's also another form of reaction, which is what we would actually call a nuclear reaction, and that is where one nuclide absorbs a particle and it actually becomes radioactive as a process of doing that, or it's converted in, even if it's not radioactive, it's converted into another element, but there's almost always some radioactivity that's given off. And one of the most common ways of doing this is actually by absorbing a neutron. So it turns out, for instance, that and the example that your book gives is that molybdenum 98. Erase all of this again, so we have some clear board. So the element molybdenum which is 42 can absorb what we call a thermal neutron. It's a neutron that's been slowed down a little bit. Neutrons are usually moving very, very rapidly. We can slow this down by passing it through something like heavy water in a nuclear reactor, or we can even, if we wanted to do this in the lab, we can use a block of paraffin, a special kind of paraffin that's got some boron compounds absorbed into it. The boron acts as a mediator that actually slows down the neutrons. And so you can see we're just going to add these things up and we're going to get 99. We're still going to remain at 42, so it's the same element. It's 99. But I believe, let me think about this for a second. Yes, I believe it's this element here that actually then is going to spontaneously decompose to give us technetium 99, probably 99M. What's going to happen is one of our protons is going to convert to a neutron. So that would be positron emission, I guess, and that would give us, let me think about this for a second. No, I'm sorry, a neutron is converting to a proton. Yeah, so this is just standard beta decay. So this gives off a beta particle, and it's going to go to technetium 99, the metastable state, and then of course that's giving off a gamma. I should write that as plus gamma, not that it's absorbing that. So plus beta, and then this is going to go to technetium 43, 99, and there's going to be a gamma given off there. So this is a way that we could actually take the normal stable isotope of molybdenum in a nuclear reactor, have it absorb neutrons, and then produce this new man-made element, technetium. Okay, so what makes things stable? If you look on page 7, you'll actually see something that shows you, it's a little table. It shows on the x-axis neutron number, and it shows the atomic number the number of protons on the z-axis. And you'll notice that there's a, you've got a straight line in there, which is actually would indicate a 1-to-1 ratio of neutrons to protons. And you'll find that you get that for the lower elements up to about element maybe 18 or so, and then it starts to what is called either a belt or a zone of stability, a band of stability, actually starts to bend away from that straight line. So basically, elements that are going to fall into that band, that is, that are going to have the correct number of neutrons, all the isotopes that are actually going to fall in that band are going to be the ones that are stable. It's a fairly narrow belt, but if they fall outside of that band, then they're going to be unstable. And we know that, for instance, I've already mentioned that very, very large atoms, they just become unstable because as they get bigger and bigger, it's just harder. These strong forces that I was telling you about, because now what's happening is as the nucleus gets bigger, the distance between a proton and a neighboring proton, because of the increasing size of the nucleus, becomes a little bit bigger, and that strong force is starting to dissipate, and that makes that actually makes the atom itself, the nucleus, a little bit less stable. But for the smaller ones, where we actually have to worry about this proton to neutron ratio, there is something else that's kind of interesting. And if you look at table 1.1 on page 8, you'll see that that there are a lot of stable nuclei for elements that have an even numbered Z and an even numbered N. That is to say that they have paired protons and paired neutrons. And so it seems to be important that these things actually occur in pairs, because if they are paired, it tends to give the nucleus greater stability. They like to occur in groups of 2. It might be somewhat analogous to the fact that it takes 2 electrons to go into a suborbital in order to fill that orbital. They have to pair off. So in the same way, these other nucleons, these other particles, they like to occur in pairs as well. So when we have both an even number of neutrons and an even number of protons, we get the greatest number of stable isotopes. There's 159 of them. If we get an even and an odd, or an odd and an even, that is, whether it's an even number of protons and an odd number of neutrons, or an even number of neutrons and an odd number of protons, we get about the same number of stable isotopes, about 50 to 53 of them. But when both the Z and the N, when both the number of the protons and the number of neutrons are odd, this it creates a very unstable type of situation, and we find out that there's only 4 stable isotopes, and those are peculiar in themselves, because the 4, and I think they're listed somewhere in the book, but they turn out to be 4 very, very lightweight elements. Here they are. They're deuterium, which is one that I already mentioned previously, which has 1 proton and 1 neutron. And then lithium-6, which has 3 protons and 3 neutrons. Boron-10, which has 5 protons and 5 neutrons. And nitrogen-14. So those are the only 4 exceptions, the only 4 isotopes that are known that have odd numbers of protons and neutrons, and they still are stable. But all other ones are going to be radioactive. So your book just says even is good and odd is bad. And we talked a little bit about why that is. Now, ionizing radiation refers particularly to those forms of radiation that will actually kick off, and I'm now on the bottom of page 8, section 1.5. This refers specifically to those forms of radiation that have sufficient energy to either, and this would be very, very unlikely, to knock, let's say, a proton out of the nucleus of an atom. That I can't even think of an example where that would happen, but that, conceivably, if you had something with enough energy, a large enough particle, perhaps, probably not any form of ion of what we would actually call radiation, but some kind of particulate something that could actually strike the nucleus, it might break off a proton. Unlikely, it would probably break off a larger piece than that, but that is a possibility. But much more likely that one of these particles or this electromagnetic radiation would actually hit an electron and knock it out of its orbital, and that would actually produce an ion, an electrically charged particle. So this is what we mean by ionizing radiation. So all of the forms of decay, radioactive decay, alpha, beta, and gamma decay, once these particles are emitted, or the photons, when they interact with matter, they're all going to have some tendency to cause ionization of whatever it is that they strike. So the alpha particle itself is an ion. It strikes something else, it's going to become ionized. The beta particle is an electron. It has an electrical charge. It can actually ionize other things as well. And the gamma, because it is a very, very high energy photon, is also capable of ionization. But as your book points out, these things differ very, very greatly in their ability to form ions. So alpha particles are the most, in terms of what we would refer to as specific ionization, they have the highest values of specific ionization. That is, an alpha particle is much more likely to form ions than a beta particle, and a beta particle considerably more likely to form ions than gamma. So in terms of ionizing radiation and what we worry about, which is ionizing radiation, that's really what causes us a lot of health problems. And I'm on page 10 right now, section 1.6, talking about a biological threat. And in bold here, you'll see a term, it's an acronym, ALARA, A-L-A-R-A, which stands for as low as reasonably achievable, which means that in terms of radiation exposure, you'd like to get it as low as you possibly can. We can't get it to zero. It's not possible. If you want to be in a situation where there's zero radiation around you, you have to leave this universe. You can't go into a very, very deep mine shaft somewhere in the center of the Earth. You can't go out into deep space. That's even a worse place to be because you're going to be hit by cosmic radiation. But there's no place in the universe that you can go where you are not going to be exposed to radiation. And even if you were to actually go to that very, very deep mine shaft where you could block out most of the cosmic radiation, you'd still have a problem because your bodies are naturally radioactive because they contain things like potassium-40 and carbon-14, naturally occurring radioisotopes that are present in everybody's body. And it's just, so we have to allow for a certain amount of radioactivity regardless. I realize this lecture is running very long, and I want to try to cut this off. I'm not going to say too much more about this. We're almost at the end of this, but I just wanted to just introduce you to this fast business about the ALARA, the idea of trying to get to the lowest possible levels. And you'll notice that he's got a little table here where he's got risk on one side and dose, radioactive dose, on the other side. And it kind of goes like that. And then there's a sort of an area in here where there's a certain amount of uncertainty. Because we can't get the dose down to zero. We'd like to believe that if we actually could get the dose down to zero, the risk would fall to zero. So there must be a certain finite risk that's associated with that, but it's actually quite low. We know in a certain range of radioactivity, we know that there's going to be biological effects. Down here, there's a certain amount of uncertainty. So that's why we say as low as reasonably achievable. One other thing, I said there's a lot of naturally occurring isotopes. I mentioned a couple of them, carbon-14, and these are things that would normally be in your body. And the other one was the potassium-40. But there also are three isotopes, thorium-232, uranium-235 and uranium-238, which have been around for very, very long periods of time, probably since the beginning of the creation of the Earth. And most of these things are going to date back. Many of these isotopes have been around for billions of years. But it turns out that all of these isotopes are not things that we really particularly worry about in terms of our health. Well, at least not directly, because we're usually not coming in contact with them. Most of you are not going to be coming in contact with these particular materials. In my area where I am right now, or maybe probably a couple hundred feet from here, in another part of my office. It's actually not my office, but it's where I'm storing some materials. I have a small amount, about 15 grams of uranium-238, the metal, which is something that I purchase legally. It's something that I'm allowed to have, but it is radioactive, and I don't keep it. I'm actually in my home right now. I don't keep it in my house. It's in my garage, and it's in an area that's well ventilated, because these things also produce things like radon, which is a gas, and we'll talk about that later on. And this is something that can be dangerous. So basically, I want to just call your attention to the U-238 uranium decay series, which is shown on Figure 1.5. And there are these what we call decay chains, where one element it goes to another element. And what I can tell you, just looking at this, you'll see that at the top, the extreme right-hand side of this picture, we've got uranium-238. It's giving off an alpha particle. Anytime an alpha particle is emitted, let me see if I can get this up close enough that you can actually read it. I don't think you can. No, I basically can't even see this image. But if you're looking at page 11, let me try to draw it. It might be easier to see. Okay, so you see something that looks sort of like this, and then it goes down, and then there's some complicated things here that look like this, and like this, and there's one down here that's kind of like a double, looks like this, and that. This represents a decay series. Anytime you see motion in this direction, that is, where it's sloped this way and it's going down, that's showing you alpha decay. Where you see it popping back up or going this way, that's beta decay. So you can see, looking at this, it's starting out with uranium-238, which is 238. That's going to go to thorium, which is going to be 90, because it's giving off an alpha particle, 234. And then it's going to, then one of the protons is going to convert, one of the neutrons is going to convert it to a proton. That's going to make this 91, which is protactinium. That's actually, it's right here. There's two of them here. That's protactinium, Pa. And then protactinium is going to give off another one, and then we're going to be at uranium-234, another uranium isotope. And then there's a whole bunch of alpha decays here. So uranium goes to thorium, goes to radium, goes to radon, and then it goes to polonium. And polonium has two methods of decay. It can either lose an alpha particle where it goes this way, or it can lose a beta particle and go that way. I'll have more to say about that later. I don't want to really dwell on that. My lecture, which I told you would be an hour, is now running to about an hour and a half. And I apologize for that. This will probably be the longest lecture you'll ever see. And I'm just about done right now. So I'll have a couple, just one or 2 minutes more. Talks about radon in here. You should read that. Radon is probably, of all the radiation that we're actually absorbing, you can see on the table on page 12, figure 1.6, that the dose, which is measured in millirem, that stands for radiation equivalent man, the rem, but it's a certain amount of radioactivity per year. So it's saying that we get 200 millirems per year from radon, and everything else, rocks and dirt, cosmic rays, our bodies, X-rays, nuclear medicine, consumer products, etc., those things probably add up less than we get for the dose of radon. but they're still relatively insignificant altogether. Finally, there's a chart of the nuclides up to carbon, from hydrogen to carbon, all the nuclides. You can see the ones that are stable are in white. All the gray ones, this is on page figure 1.7 on page 11, all the gray ones are the ones that are radioactive, the chart of the nuclides. And that's basically the whole chapter. So I don't expect you to memorize atomic numbers or atomic masses. When I give you the chapter, I'm going to give you a table, or I'm going to give you something where you can refer to these things. I'll give you a periodic table or something like that. You don't need to know that, but you should know the other laws and rules that we've been talking about. And thank you very much for your patience. And as I said, in the future, I'll try to cut this a lot shorter. Thank you.